Hello everyone. We're actually going to skip section 5.5 and move on to the very last thing that accelerated pre-cal always does, and that's just to get a little introduction to calculus. We're going to talk about some limits, maybe get to continuity, mainly just trying to get into limits and the very first part of calculus. So everyone thinks that calculus is a really difficult thing, but really there's only two parts in the Calc 1. The first whole entire half of the year is just doing something called the derivative. And the derivative is just finding the slope of a tangent line. And if you remember back to geometry, like a tangent line just means like if I'm right here, tangent is just touching in one spot. So that would be a tangent line right there. If I'm right here, the tangent line would be like that. So just basically finding this tangent line at different spots on the function. As you can kind of see, going through the function, it should only be touching one spot, and that's locally. So like right there, yeah, it's touching there, but it's also touching here. We just mean locally, like right by it, by the actual point. So that's the whole first half, and it has a bunch of applications to it. If you take calculus, you'll actually get into those. Finding the acceleration of something if you're given the velocity, or finding the instantaneous flow of out of like a garden hose, like how much water is coming out at a very precise moment. That is basically the derivative. Okay, there's two notations to it because there was actually two people that discovered calculus, and they discovered it around the same time. This notation right here comes from Isaac Newton. This is f prime of x. That's how you would read that. There was also someone with the last name of Leibniz. This is his notation right here. This is dy dx is how you would say it. This says derivative of y with respect to x. Okay. In calculus, you'll see both of these notations and you'll use them interchangeably. Sometimes it's better to use Newton's. Sometimes it's better to use Leibniz. Okay, you can be on Team Newton, you can be on Team Leibniz. It really doesn't matter. Either one would work. So that's the whole first half of calculus, just finding that tangent line as we go. Okay. The second half of calculus, that is called the integral. And the integral looks like this. If you've seen that little symbol, kind of looks like an S. You also see them on like violins a lot. For an integral, all it is just the area under a curve. So if I was wanting to find the integral from, say, 0 to 2, that would be a 0 and that would be a 2. It's just this area right here. Under the curve, but above the x-axis. Okay, and then that's of our function with respect to x. Okay, if I was trying to do the integral, that's what that one is right there. If I was trying to do the integral of, say, here to here, that would be from 4 to 5, 4 to 5. This would be our area under the curve to the x-axis of our function with respect to x. Now, this would be positive because it's above the x-axis. That would be negative because it's below the x-axis. You'll learn a lot more about that in calculus. Right now, that's not super important. I just wanted to show you basically what calculus really is. The first half is just finding the tangent line. Second half is just finding the area under the curves, and that's it. Okay? Don't want to scare you. All right. So let's kind of get into that very first part of calculus, that whole derivative, and that's a word that you really need to know, derivative. And that is going to be our watch code for the day, is derivative. It's a really important one. It's the whole first half of calculus, so you need to know it. So our question is, what is the slope at 2? So at 2, this point right here, what is the slope? Well, this isn't linear, so the slope changes. Like right here, the slope is actually 0. If I draw on a tangent line, the slope is 0. right? Right here, it's positive. It's going up. I want to know at 2. So right here, what is this slope? Okay, we know it's positive because it's going up on both sides of it. But what is it? So pause your video, think about it for a little bit. How can we find the slope at 2? Okay, hopefully you thought of something. Maybe you said, well, we could approximate this just by finding this, finding the slope from 2 to 3, from here to here. That would give us a pretty good idea, because that would give us basically how far it's going up. So this would be f of 2. Well, f of 2 is just 6. F of 3 is 11. So we can just find the slope between those 2 points. y2 minus y1 over x2 minus x1, and figure that out. y2 minus y1 over x2 minus x1. That would give you 5 over 1, which is just 5. Okay, pretty good approximation. Try to make it better. All right, so pause your video, try to get a better approximation. Okay, so hopefully now you're saying, well, there's really nothing making it where we have to go from there to there. Let's try to make it a little bit better and bring it in. So instead of there, let's try there. Okay, so then now it's like this. A little bit of a better approximation. So from here to here, that would be like 2.5. So we still have 2 for an x value. Then we also have 2.5. 2.5 is 8.25. All right, if you do the slope formula with that, y2 minus y1 over x2 minus x1, you actually get 4.5 for your slope. Okay, so we went from 5, that was our first approximation. Then we brought in this point a little bit, we brought it down to there. It gave us a little bit of a better approximation. Let's try to make it better. All right, well, you're thinking, let's scoot it in again. Let's do like 2.25. Okay, and I would say, well, we can make it a little bit better. And then you say, okay, make it 2.2. And then I would look at you and say, make it a little bit better. And then eventually someone's going to say, okay, well, we got 2. Let's try 2.01, something like that. All right, if we try 2.01, that gives you 6.0401. And if you do the slope formula with that, y2 minus y1 over x2 minus x1, you get 4.01. Okay, and eventually we would kind of see these numbers getting closer and closer. We started off with it as a slope of 5, and then we brought it in as a slope of 4.5. We brought in a little bit more. I didn't really go over what those were. I was wanting to cut down some time. It would have been 4.1. And then we brought it even closer in. Now the second point's like right here. And we got it to 4.01. So you're probably saying, I think this number would actually go to 4. And we would actually, if we were in class, we would keep making this number smaller and smaller. We would say, try 2.001, 2.0001. And you would see this number get closer and closer and closer to 4. Actually, the slope of this, the tangent line, because that's what the instantaneous slope is just a tangent line, that is 4. Okay, well, you could do some calculus. It would be really quick on this one to do the calculus. The slope is 4. At, I don't know, say 1, 2, 3. At 4, way up here, the slope of that would actually be 8. If we were all the way at like 30 for the x value, the slope at 30 would be 60. Okay, and you might see a little pattern. If you have some friends in calculus, they would tell you the very quick way to do this. I don't want them to tell you yet, though. You need to get some basics down first. All right, well, let's kind of try to generalize that a little bit. So what is the slope at, say, x? Like this was our 2 before. So at this point, what is our slope? What is that tangent line? That's what we're trying to find. Okay, well, think about what we were doing before. We started off with a point really far away. Let's call that, I don't know, just a second point. I want to call it x2. Let's call it, if this is x, let's call this x plus h. X plus some number. So in the previous example, we started at 2 and then went to 3. So that would have been 2 plus 1. And then we brought it in a little bit. It would have been 2 plus 2.5. And then we made it smaller and smaller and smaller. So from here to here, this is going to be h. And then to look at these points, well, let's call this point just f of x. So this would be x comma f of x. This point right here would be x plus h for your x value. And then your y value would be f of x plus h. If we try to just do the regular slope formula, so this is basically the exact same thing that we were doing before, like this was 2 and this was 3. Think of it like that. If we just try to do the basic slope formula like we did before, is y2 minus y1 over x2 minus x1. And we can simplify this a little bit. So the x is down here, x minus x, those are going to actually cancel each other out. Okay, and really what we were doing before in that example is we were trying to bring that closer and closer and closer to where that h value would get smaller and smaller and smaller. So we started off in that previous example, we started with 1 was the difference here, and we kept bringing that second point in, and as we brought that second point in, that gave us a really good approximation of what this slope was, what the derivative actually was. So the question is, well, what happens as it gets basically, as the h value approaches 0? So as we bring that point in closer and closer and closer to this, to where it's basically on top of itself, what would that be? Okay, so you're probably thinking, well, let's just plug in a 0 for the h. Like if you plug in a 0, plug in a 0, you'd have f of x plus 0 minus f of x over 0. Well, f of x plus 0, that's just f of x. F of x minus f of x, that's 0. And on the bottom we have 0. And that kind of makes sense, because if my first point and second point are the same, I'm not going up any, and I'm not going left or right any. So my rise is 0, my run is 0. And the question is, well, what is this? Is it 0? Because 0 divided by anything is 0? Not exactly. Is it undefined because you're not allowed to divide by 0? Not exactly. Is it infinity? Because if we think about the graph of like 1 over x, the graph of 1 over x looks like 1 over x looks like this. So like infinity, negative thing, we don't know. So it actually depends. Sometimes it's a number, sometimes it's 0, sometimes it's infinity, sometimes it doesn't exist. So really you just have to know the calculus in order to do it. If you take it next year, we'll get into that. Okay. This is the definition of the derivative. Definition of the derivative. The only thing that we're missing is this little part right here. This has the limit as h approaches 0. What this is saying is as h gets really, really small, as this amount gets smaller and smaller and smaller, this would give you the slope of the tangent line. That slope right there. As we bring this point in really, really close and we make it approach 0, that distance is approaching 0 from here to here, that gives you the slope of that tangent line. That's the very first part of calculus. This is something that you need to memorize if you're going to take calculus next year. All right, one last thing. So we have our function. I want to just basically evaluate kind of the derivative. We're not going to do the limit part yet because we don't know what a limit is. Hopefully we'll be able to do that before we're actually out for the rest of the year. So all I want to do is just simplify this. Okay, this is actually on your weekly review sheet. That's going to be your homework, is to do 1 and 2 on your weekly review sheet. Other than that, you won't have any other homework to turn in for me for this video. Just 1 and 2 on your weekly review sheet. So this is actually something you kind of saw it in Algebra 2. If you remember, like composition of functions, where it's like f of g of x or f of x plus 2, and you just plugged in. Like for this, you would plug x plus h in for here and here. That's basically all this is, okay? If you can do that, then it's actually not that bad. So this says f of x plus h. So x plus h is going in here and here. F of x, that just means it's staying the same, over h. So to figure this out, we're going to plug x plus h in here first. Then it's minus f of x. So minus the thing as it sits. Hopefully you just kind of saw a mistake that I made. You need to put parentheses around it because you're subtracting the whole thing all over h. And then all you have to do is simplify, and simplifying is actually going to be the hard part about this. So this part you're going to have to use FOIL. So it'd be x squared plus 2xh plus h squared. This piece you're going to have to distribute, so it'd be minus 3x plus, or no, not plus, minus. You'd have to distribute this inside. And if you did everything correct, a ton of stuff should cancel. So like this x squared and this x squared cancel. And that's always going to happen on these definition of the derivatives. A ton of stuff cancels out. Let's see, 3x and 3x. Those are going to cancel. Plus 5 minus 5. Those are going to cancel. All right, so we have 2xh plus h squared minus 3h all over h. All right, we're still not finished because actually what we can do, all of these have an h. So technically what we can do is factor that to the outside, and those h's are going to cancel. Or you could think every single one of them has an h, so you can cancel out one of the h's on all of them. So for this first piece, it'd be 2x. That piece right there would just be h. And then those h's would cancel. So this is actually what it simplifies down to. If we could take the limit as h approaches 0, that would be the derivative at any point on that graph. Like if I wanted to figure out what is the slope at 7, I would plug a 7 into this derivative function, and then that would tell us the actual slope. Okay, it's 11. Spoiler there. So that's it for today. Make sure that you do those first 2 on the weekly review sheet. Turn it in hopefully tomorrow. Thursday I will have another video for you to watch. Until next time.